Dear children, in the previous class I have explained you the vapor pressure and the lowering of vapor pressure when a non-volatile solute is mixed in a pure solvent. Once again I want to define vapor pressure. Vapor pressure is defined as the pressure exerted by the vapors on the surface of the liquid at equilibrium. Now, when we mix a non-volatile solute in a pure solvent, this non-volatile solute particles, they occupy the surface and the bulk. And due to this, the fraction of the solvent particles on the surface decreases, and hence they get less chance to escape and to convert into vapors. Just see this picture. In the picture A, you can see that it is a sea water, and sea water has many salts. You can see the red balls, these are water molecules, and yellow and white balls, these are some salts. Now, due to these salts, the water molecules, they are in lesser number on the surface and they are getting little chance to escape. So, in the vapor state, the number of the water molecules are less. In the figure B, we have pure water. There is no salt. So, on the surface, totally we have the water molecules and they are getting greater chance to escape and to convert into water vapor. So, now you can compare the two figures and can very well know and understand that there will be a lowering in the vapor pressure when a non-volatile solute is mixed. It's very important to understand this because there are many properties which depend upon this factor, and these properties are known as colligative properties. Today we will study about these colligative properties. Colligative properties of a solution which are dependent only on the number of the particles in solution, not on their nature. The four colligative properties are the relative lowering in vapor pressure, elevation of boiling point, depression in freezing point, and osmotic pressure. We will discuss one by one. The first colligative property is relative lowering of vapor pressure. Just now in the beginning I have explained you that there will be a lowering in the vapor pressure when I will mix a non-volatile solute in a solvent to make it a solution. This relative lowering of the vapor pressure is a colligative property because it depends upon the number of the solute particles. More is the number of the solute particles, more is their concentration, more its molarity, the more will be the lowering in the vapor pressure. Mathematically, P01 minus P1 upon P01 is equals to W2 into M1 divided by M2 into W1. This P01 is the vapor pressure of the pure component 1. Here 1 is a solvent. P1 is the partial vapor pressure. The component 2 is the solute. Now you can see from the formula that it is molality. W2 into M1 divided by M2 into W1. So, more is the number of the particles, the solute particles, more will be the lowering in vapor pressure. This property is very important to understand because rest of the colligative properties entirely depend upon this lowering in the vapor pressure. The second colligative property is the boiling point elevation. Before starting this, let me tell you what is boiling point. We know that when a liquid boils, it changes into vapor state. In the junior classes, we say that it is the temperature at which a liquid changes into vapor state. But at the 11th standard or in the class 12 standard, we must also add that it is the temperature at which the vapor pressure becomes equal to atmospheric pressure. When both these pressures are equal, that particular temperature, the liquid starts boiling and it changes into vapor state. Now, what is elevation in boiling point? Actually, what happens? The vapor pressure lowering takes place when we add some solute to a pure solvent. For example, water boils at 100 degrees Celsius. It means at 100 degrees Celsius, the vapor pressure of the pure water is equals to the atmospheric pressure. But when I'll mix a non-volatile solute in water, for example, I mix glucose or urea or sodium chloride. These are the examples of non-volatile solute. Obviously, when I'll mix these solute particles, they will go into bulk and they will come on the surface. And when they will occupy the surface, then the water molecules will get less chance, or you can say that the fraction of the water molecules on the surface is decreased, and hence there is a lowering in the vapor pressure. Due to this lowering in the vapor pressure, it will not boil at 100 degrees Celsius. We have to heat it more to make this vapor pressure equals to atmospheric pressure. And now we are heating our water more. That means what? Elevation in boiling point. Let me explain you through a graph. The graph is between temperature along x-axis and the vapor pressure along y-axis. You can see two curves. One curve is for a pure solvent, that is AB, and another curve is for the solution, that is CD curve. From the figure only you can see that the CD curve is below AB. This shows that at each temperature, the vapor pressure of solution is less than the vapor pressure of the pure solvent. Now, from the graph you can see that T naught B is the boiling point of pure water, because at T naught B, the vapor pressure is equals to atmospheric pressure. Just see the point B. And at this temperature, the pure solvent will boil. But in the case of the curve CD, that is the curve for the pure solvent, at the temperature T naught B, the vapor pressure is very less than the atmospheric pressure. So, the solution will not boil. And if we want our solution to boil, we are heating it more. And at TB temperature, the vapor pressure increases, becomes equals to atmospheric pressure, and at point D you can see that it is becoming equal to atmospheric pressure and it is boiling. So, you can very well see that there is an increase in the boiling point, and this increase in the boiling point is known as delta TB, that is elevation in boiling point. It is equals to TB minus T naught B. Now, elevation in boiling point is a colligative property. Now, why it is a colligative property? Just in the beginning I have told you the colligative properties are those properties which depend upon the number of the solute particles. It is also depending upon the number of the solute particles, so it is a colligative property. More and more we are going to add solute in the water, more lowering of the vapor pressure will be there, and we have to heat it more to make its vapor pressure equals to the atmospheric pressure. So, there will be a higher value of the elevation in boiling point. Now, mathematically you can see delta T is equals to I KBM. Here delta TB is, or delta T is, the elevation in the boiling point. I is Van 't Hoff's factor, which I will explain you later on. KB is molar elevation boiling point constant. It is also known as ebullioscopic constant. Its unit is Kelvin kg per mole. and M is molality. Molality, you know that it is the number of the solute particles in 1 kg of solvent. These are some sample ebullioscopic constants. For benzene, the value of Kb is 2.53 Kelvin kg per mole. For camphor, it is 5.95 and so on. For water, it is giving 0.52. These values are important when you are going to solve numericals based on elevation in boiling point. For the common solvents, it's better you must learn the values for at least benzene and water. Mathematically, delta Tb is equals to Kb into W2 into 1000 divided by M2 into W1. Here you can see that delta Tb is inversely proportional to molecular mass of solute, and from this formula we can calculate the molecular mass of any solute, and if the molecular mass is higher, the value of delta Tb will be lower. Now let me revise what we have studied just now. The lowering in the vapor pressure on mixing a non-volatile solute to a pure solvent, and there are many properties which are known as colligative properties which depend upon this lowering of the vapor pressure. These colligative properties depend upon the number of the solute particles and not on their nature. The relative lowering in the vapor pressure and the elevation in boiling point are the two colligative properties just now I have discussed. In exams, we get a graphical question, and elevation in boiling point graph is very important in that respect. Also, the numericals based on these formulas to calculate boiling point of the pure solvent or to calculate the boiling point of the solution. In this regard, you have to keep in mind that the temperature, if given in degrees Celsius, just convert it into Kelvin by adding 273. It is the most common mistake children do. I hope this is all very much clear to you. Thank you.